Good afternoon, guys. This is the first audio lecture, and this will be about convolutional codes. And I'll be posting a series of audio lectures on unit number 8. It is on basics of convolutional codes and encoding using time domain approach, transform domain approach, and graphical approach, and Viterbi algorithm. So let us see about convolutional codes. And our unit number 7 and 8 started with error control codes. So we already know that error control codes are used for adding the capability to your messages, the capability of error detection and correction. So simply by adding some redundancy, we will give our messages the capability for error detection and correction. So under that error control codes, we already discussed block codes, and second one is convolutional codes. Block codes we already discussed it. So linear block codes, and they are systematic codes. Suppose in block coding, let us say this is the encoder. So the encoder accepts k bits as a block and produces a n bit code word, and as we said, this linear block codes are systematic in the sense the k message bits, they appear as they were in the output. I mean, the first k bits are the message bits, and the last n minus k bits are the parity bits or check bits. So in block coding, we are taking k bits as a block. So there is a necessity for storing these k bits as a block in a buffer. As the block size increases, the buffer size also has to be increased. So this is a problem in block coding. And a block code is generally denoted by n comma k. So n comma k, where n is the number of bits in the output code word, where k is the number of input bits as a block. Whereas coming to convolutional codes, so convolutional codes are also used for error controlling purpose, and I mean we can detect and correct errors. I will later tell you the name why the name has come as a convolutional encoder. A convolutional encoder, it takes k bits as input, but these k bits are not given as a block. The convolutional encoder processes these k bits in a serial manner, so instead of processing as a block, and it produces output n bits. So the only difference between block codes and convolutional encoder codes is in block codes the k bits is processed as a block, whereas in convolutional encoder the k bits are not processed as a block, but they are processed in a serial manner. So this eliminates the necessity for using a buffer. And how a convolutional code is specified, and we know that a block code is specified as by n comma k, whereas for representing a convolutional code we need 3 parameters. The first parameter is n, number of output bits, and k, number of input bits, and capital K, constraint length. So when you are specifying a convolutional encoder, you need to specify these 3 parameters, or we all know that the rate of a encoder is given by k by n. This is what we call as rate or efficiency. So let us say a convolutional encoder takes one input bit and produces 2 bits. Then we call the convolutional encoder as rate 1/2 convolutional encoder. And coming to constraint length, so in just few minutes we will be looking at the basic structure of a convolutional encoder. So after going through the structure of the convolutional encoder, we will come to know what is this constraint length capital K exactly. Okay, so now knowing the fact that convolutional encoder is also used for error detection and correction, and it takes k bits but processes in a serial manner and produces n bits. Okay, and now let us go through the basic structure of a convolutional encoder. So what does a convolutional encoder will consist of? A convolution encoder generally consists of a shift register, and we all know that shift register is made up of memory elements, which are nothing but flip-flops, and then modulo 2 adders. So a convolutional encoder basically consists of a shift register, which is made up of memory elements, and then modulo 2 adders, and the inputs and the outputs of the flip-flops are in some way connected to the modulo adders to produce the outputs. Now let us see a simple example of a rate 1/2 and capital K equal to 3 convolutional encoder. So as we discussed, we need to specify these parameters for a convolutional encoder. So rate 1/2 means one input bit, 2 output bits, and capital K equal to 3 is the constraint length. So let us rather a simple example. So now this is the input, and a memory element, one more memory element, and this dot represents a connection. So now as it is 1/2, there are 2 adders. This is the output of the first adder, first output, and then second output, and at the output there will be a multiplexer or a switch to connect between these 2 outputs. Now if we see the structure, so we have 2 memory elements and 1 input, and so we got 1 input and we got 2 outputs and 2 memory elements. So as said earlier, the rate is 1/2 because of 1 input and 2 outputs, and there are 2 memory elements. Now let us consider a input present here. Let us say a bit is present here, 0, let us say. So the constraint length is can be defined as the number of memory shifts required for the input bit to influence the output. So let me write that. So capital K, the constraint length is the number of memory shifts required for the input bit to influence the output. So in a simple way. So there are other ways to define constraint length, but this is the simple way of remembering it. Now let us see this. So if a input of if a input bit is present, so for one clock pulse there will be a shift. That means for one shift this input bit will be in the first memory element. For the second clock pulse it will be shifted to the second memory element. For the third clock pulse it will be shifted to the influence the output. So for this structure of rate 1/2 with two memory elements, for the input bit to influence the output, 3 memory shifts are required. So in this example the memory, so the constraint length is capital K equal to 3. In general, for a single stage shift register structure of convolutional encoder, the constraint length K is given by m plus 1. So here m is the number of memory elements. So this is the basic structure of a convolutional encoder, and if you look at the structure carefully, the outputs 1 and 2 depends upon the present input as well as the previous inputs also. That means in this case the outputs depend upon the present input as well as the last K minus 1 inputs also. K minus 1 means here capital K. Suppose let us say capital K equal to 3. So the outputs depend upon the present input as well as the K minus 1. K minus 1 means 3 minus 1, which is equal to 2. So for the given encoder structure, the outputs depend upon the present input as well as the last 2 inputs also. So whereas if you look at a block code, so the output code what is produced depending upon the particular input message block. It doesn't depend upon the previous message blocks. Whereas coming to convolutional encoder, so the outputs depend upon the present input bit as well as the previous K minus 1. K minus 1 means capital K minus 1. So the present input as well as the previous K minus 1 inputs. So that is how a convolutional encoder structure is. So basically any convolutional encoder will consist of a shift register, either single stage or depending upon the number of input bits, and a modulo 2 adders to produce the outputs. Okay, so next we will look at the encoding process. So the encoding process can be done in 3 ways: time domain approach, transform domain approach, and graphical approach. So in the next audio lecture I will be discussing about the time domain approach, and after that I will be discussing transform domain approach. Thank you.